To create a function, you first write the return type. So for example, we can return a float, and then you write the name of that function. For example, do something, and then you open a bracket, and then you provide the parameters which this function wants. It can obviously take no parameters at all, but we'll take some parameters over here. And to take some parameters, you first define the parameter type. For example, it can also be a float type. Then you have to define the parameter name. You can name it give, and you can obviously grab more parameters by separating them by comma. So type a comma, and after that you can take more parameters, and just like that. But we don't need more parameters, we will only take one parameter. And then to define that function, you have to open a curly bracket, and inside that you define the function, so you write what it does. So for example, we can take our give parameter which we have, and then add 1 to it, 1.0, because it is a float, 1.0f to make it 32-bit. And then to return it as the result of the function, you have to use this return keyword. Now it will return this. And obviously it won't do anything right now because we are not calling it inside our kernel, but we can call it. So for example, right now we have this var variable which stores our current pixel value for which our kernel is running, and we can call our this do something variable on that and set it to this var variable back again. So we can say var equals do something, and then you open bracket and give that argument. So it can also be var, and we will close it, and we will set our var to that. And now you'll see that. And obviously I forgot that it is a float 3 and not a mono layer which should be float. So we have to set it to float 3. So if we set the display flag on it, as you can see, everything gets 1 added to it. If we inspect, as you can see, we have 1 added to everything. We can also reduce it to actually see that what it is doing, 0.2, and as you can see, it is adding a constant value to it. But one thing which looks very weird over here is that we are taking the var and applying that do something function to it, returning it, then again storing it to the var. This is too big, and we can simplify this by taking pointers as our parameters in for this do something function, and return nothing, but we'll modify that parameter directly, because that will be a complete reference to that special that variable, and then we'll be able to modify that, and then it will work. And to do that, we'll first remove this line. And now, because we don't want to return anything right now, because as I said, we will directly modify our parameter. So to not return anything, you can use the void return type, and that means that you won't return anything. And now we can remove this return, because we can't return this float 3 value. We just have to quit this function so we won't return anything. So we can just only say return. We don't need to return this, and we'll say give equals give plus 0.2 f. And now if we call this do something function on this variable, you will expect it to work because we are taking this parameter, this give parameter which we provide over here, this var, and then we will add 0.2 in that, and then return from that function. but it won't work because this parameter will create a copy of that. And to avoid that, we can use pointers. And pointers are basically an address to something in the memory. So to make this an pointer, we have to use this asterisk sign after we write our data type. And now what it is doing, that it is expecting an address as an parameter, a memory address which has a float 3 data type. So we have to pass a address over here and not directly this var. And to get the address to this var variable, you have to use a AND sign before this, which will give you the address to this. So this entire thing will give you the address to this variable in the memory. And now we are passing that in this do something variable. And now on that address, the variable which lives there, we can modify that. And to do that, we need to modify that value on that address and not the address itself. So currently what we are doing is we are modifying the address. So we are adding 0.2 to that address, but we don't want that. And to modify that value instead, you write this asterisk sign over here, which is called dereferencing, and it will give you the value on that memory address, and then you can modify that. And again, we have to dereference it over here, and now it should work. As you can see, we are adding the 0.1 constant, and even if we are not returning anything, we'll directly change this variable which we are passing as a input, and we'll modify that and it will work. And I know that this entire pointer thing is looking very weird, but it is important to know this because it is very useful in OpenCL. And now since we know this, we can remove these lines now. And now we'll learn about how we can access the current pixel coordinates. And to do that and visualize it, we will first make our output a float 2 or a UV. So we can set it to float 2. And now we'll remove these lines and we'll make this float 3 a float 2. And first of all, we'll try and access the buffer space coordinates. And to access the current pixels buffer space coordinate, you use the @ixy, and this gives you the index of the current buffer space coordinate, and it gives you the both x and the y coordinate, which returns in 2. So we have to convert it to this float 2 to visualize it. And to do that, instead of accessing this in 2 coordinate, we can access the x and y coordinate differently, and then we can convert it to a float 2. And to do that, we'll first set up our converter. So float 2 in a bracket, and after that we'll open a bracket again. And now to get the x and y coordinates separately, because if you directly do @ixy and try to convert it to a float 2, for some reasons that won't work. As you can see, it gives an error. We can't invalid conversion between float 2 and int 2. So to do that, we'll get the x and y component and convert that to a float and initialize this float 2 variable with that. And to do that, first we have to access them separately. So there's a accessor for that @ix and @iy. And to separate them, we'll use this comma. And then we also have to convert that to a float because it is currently a int type. And then using this comma separated values, we'll be able to initialize this float 2 variable. Now this should work. And right now the output doesn't make sense, but if you right click and go to inspect mode, you will see that we are getting the correct buffer space coordinate. So as you can see, the left bottom corner is 0 and 0, and it is currently RGB because we didn't reset the signature. So we can set it to UV, and now there are only two values. And as you can see, this corner pixel has a value of 0 and 0, that's why it is black. And as we go further in the x-axis, it goes 1 and 2 and 3, and we can access the coordinates. And when we go up in the y-axis, it also increases 6, 7, 8, 9, 10. And when we go up on the both axis, the both axis axis value increases for the current pixel. And what actually happens inside the kernel is that the pixel which the kernel is currently running for, we get that coordinate using this ix and iy, convert that to a float first, and then initialize, make a float 2 from them, and then initialize our float to variable widget and use it to set our output layer. And it happens for all of the pixels, so we get all of the pixel values. And you can also get the x and y component directly from this at ixy by using this the dot operator and accessing the x and y values. So we can do it over here too, dot y, and it will be the same, as you can see. And you can obviously do it directly inside the this set function. So you can cut it out from here and paste it over here and comment it out, and it would still work, but that's more clear to read, so we'll keep that. And now we'll learn that how we can access the image space coordinate. But before that, we want to see the difference between the display and data window, because that's what actually makes the difference between the buffer space coordinate and the pixel space coordinate. And to do that, let's first make the data window and the display window different. And currently our data window is same size as the display window. That's why we have values for all of the pixels in the memory or the buffer, and that's why the buffer space coordinate is available for all of them. But if we use a crop on this, a crop node, using this we can crop the data window. And as I said before, this space concept is used everywhere in the Copernicus context, because as you can see, it is currently taking the unit in image space. As you can see over here too, that it is taking it from -1 to 1. If you change it to texture space, then it takes from 0 to 1. You can also change it to pixel space. And what we want to do is crop the data window from above. So we'll change this, the upper right y value, and let's set this to 0. And we can also change the lower left x value to 0. And now if you middle click on this node, as you can see, we have a display window of 512 times 512 pixel, but the data window is only 256 times 256 pixel, or you can also call this 256 pixel square. And if we connect it as a input of this OpenCL node, now you will see that now our buffer space coordinate starts from our data window's left bottom corner, as I said before. So as you can see, if we turn on inspection, this lower left is corner is 0 and 0, and not something like 256. But as I said in the slides, the pixel space coordinate is not linked to this data window, it is linked to the display window, and we'll test this out right now. So to access the pixel space coordinate, we have to first say at p, and this gives us three kinds of positions: the image space position, and the texture space position, and also the pixel space position. But you can't get the buffer space position from this, so you have to use this at ixy or at ix and y for that. And to access a specific type of coordinate from it for the current pixel, you have to use the dot operator and specify the space name. So the space we want to access it for currently is pixel, and then we can access the x coordinate of that, and that's also integer, so we have to convert it to float. And we can do the same for this one at p.pixel.y. And now you will see that what I said was true, that pixel space isn't linked to the data window. As you can see, this corner value is already not black, and if you hover on it, it is 256 and not 0. And that proves our point that the pixel space is not linked to the data window, but it is linked to the display window. And now we can check it for the texture and the image space. So if we say texture over here, then we'll get the texture space coordinate. I think it is texture, or it is probably text. I don't remember correctly. Let's leave it and see. Yeah. And as I said in the slides, the texture space is linked to the data window and not the display window. So it starts from 0 over here. As I said, zoom it in a lot. As you can see, it starts from 0 and ends with not a complete one, but it ends over here. And it is not completely 1 because we are not starting with completely 1 over here too. We are starting with 0.20 over here. That's why it is this value over here. And we can also check it for the image space. And as I said in the slide, the image space is linked to the display window. So we can access that, bring image over here and image over here too. And as you can see, if it was linked to the data window, then we were supposed to have a 0 value over here and a 1 and 1 value over here, but we don't have that. And that means that it is not linked to the data window, but it is linked to the display window. So if we bypass this node, this crop node, and make the data window same as the display window, as you can see, our center is over here, and that's 0 and 0. And this pixel is 1, -1 and -1, almost -1 and -1. And this is how you access the coordinates for the current pixel. And also I showed you that how it is linked to the data and display window. And now we can do obviously some simple math with it to make some filters. We can set this output layer back to float 3 and this to float 3 too, and remove this line. Let's set it to the input first and go to the signature and change this output signature to RGB. Obviously you can clear this and make it again or using this button, but now we know that how this signature tab works, so you can use it like that. And now what we can do is that, for example, we can take the the buffer space x coordinate of the current pixel for which the kernel is running, and actually it is parallel, so it is running for all of them at the same time, as I said. And then we can use the modulus operator to don't let it go beyond a certain limit. And a modulus operator gives you the remainder of a division. So for example, if we set this to 50, then it gives you the remainder of our current pixel x coordinate divided by the this value 50, and then we can convert it to a float, and we have to put it in a bracket so that it doesn't quickly tries to convert this at ix to a float before even doing this modulus. And now if we cook this, you will see that we have these stripes, and if you inspect by enabling this inspect mode, you will see that the value goes from 0 to 49, hopefully, yeah, 49. And for the 50th x coordinate, the division remainder becomes 0 again, and then for 51, for example, the remainder again becomes 1, and just like that it goes to for this 49 or the 99th x coordinate again, and then again at the 100th x coordinate it again becomes 0, because the remainder of the division becomes 0. And now what we can also do is multiply this test parameter with this. So at test power, we can multiply that and set it to a very low value like 0.01, and now you will see something like this, which looks like a stair, for example, with ambient occlusion. And you can also move this by adding a integer value to this ix. For example, what you can do is bind another parameter, so hashtag bind, and then the data type is parm. The data name can be, for example, move. It can be optional, and it is int type, and the default value can be 0. And now what we can do over here is add that to this at ix coordinate value, and then add a bracket around this, because we don't want to do this modulus on this at move first and then add that to this our current x coordinate. And now if you bind that parameter and try to change it, this pattern will start to move, because we are offsetting our current pixels x coordinate with this move parameter. And you can also change this to the y-axis coordinate, and now this will flip, as you can see. And now, for example, you can also multiply that this pattern we generated with this this butterfly. What we can do is we can say var times equals at in. So our the current pixels, the current input pixels value will multiply our this float 3 value with it, and now you'll have something like this. And you can offset this and have some fun. You can obviously do more than just this, and we'll try that in the next part when we make more practical OpenCL filters. And now the last thing we want to look at is preprocessor and preprocessor flags. And one thing which we should know before learning about preprocessor is that this code which you write over here doesn't or directly gets applied to the image, because computers can't understand this language. They can only understand the machine code. And that's why what actually happens is that first this code gets expanded into this generated code, and then this gets compiled. And what compilation does is that it converts this code to a machine code, or the sequences of 0 and 1, which I think you already know about. And our machine can understand that, and then that code gets applied to our image. And that's what you actually saw when you turn on this timing message. So if we already have this turned on. So if we middle click on this, the compilation and the binding time took 0.43 millisecond, and then we cooked the input, and then that took 0.47 millisecond. So this compilation part happens first, and then we cook it with this input. And now before this code gets compiled, this generated code gets compiled, it runs through another step which is called processing. So what actually happens is, we first write this code, and then that gets expanded to this internal code, and then it runs through the process of pre-processing, and then that gets compiled, and then it gets cooked with this input. And that pre-processing part, you can call it a text editor, for example. So in that pre-processing part, the preprocessor looks over your code and looks for any special preprocessor flags, which we will learn about in a minute, and then does the thing which it is supposed to do with that flag. And the most basic one is the include preprocessor flag, which includes a external header file. And to do that, first we have to enable this button, this use hashtag import for prequel code. And then what you can do is say include, and then in this I don't know what you call this, just write this, it is in the corner of your keyboard. So you have to write this, and then the header name, and then that file will be included, and then it will be replaced with whatever that file has. And I know it is not making sense right now, but I will explain. So we can remove it right now. So in a file explorer, you can go to wherever your Houdini is installed, and then, for example, for me it is installed in my local disk C, and then program files, and then this side effects software folder. Inside this you have this Houdini, and then the version folder. You have to go inside it, and inside that go to this Houdini folder, and then search for the OCL folder, and this is where all the OpenCL stuffs live. And inside this folder you also have this include folder. You can go inside it, and you have a lot of .h files over here, and these files are called headers, which are a set of code which you can include in your own code, and then that would have that code which is inside it. For example, we can for example take this random, and we can preview this, and I am able to preview this because I have a plugin installed for this to preview this .h file. You might not be able to do that, so you can just open it in a normal notepad. So what this file contains is these code, which as you can see is just containing some functions, as you can see. So for example, over here we have a float, a function which returns float, and the name is sysFastRandom, and it takes a uint pointer seed. And we also have this sysvang int hash, which is a integer scrambler to scramble a seed. And we have lots of other headers over here, For example, this color.h, it has some nice functions to convert between HSV and RGB and do the and vice versa. And it also has this functions to compute the luminance. But how can we use these functions and all of the things in our code? And to do that, we have to use this include preprocessor flag. So we can say include, and then this I don't know what you call this, just write it, and then you have to write the name of the header. So it is color.h, and now we have that library included in our code, and now we can obviously use it over here. For example, we have this variable which is RGB, and we can convert it to HSV using the functions which we have over here. So we have a RGB to HSV function which takes a float 3 RGB. That's what we want. So what we can do is we can say var equals, what was the function name? Let's take a look. Vex RGB to HSV. Let's copy this. Let's copy the entire thing and then paste it over here. Oop. Okay, let's just write Vex RGB to HSV, and then we can provide our variable as a input and store the output in our variable again. And now you will see that it is converted to an HSV. And to convert that back to our RGB, we can again use the HSV to RGB function, which it provides vex HSV to RGB. Then again we use the var as an input, and that again converts that back to an RGB. So what actually happens in the pre-processing stage is that it first gets expanded to our generated code, and then this include part, this gets replaced by whatever this file contains. So this entire thing gets you can say copy pasted over here, and that's why I said that pre-processing part is just like a text editor, because it can do things similar to text editing. So as I said, it will just replace this include part with whatever that color.h contains, and then we will be able to use this function over here, and then it will get compiled, and then it will work. And also, after a code file is pre-processed, it is called a compilation or a translation unit. You should know that. And now we'll learn about some other preprocessor flags and operators, which is also very useful. And it is the define flag, which is used to define macros. And what a macro does, so we can keep this include part. We'll do some tests with it. To define a macro for our preprocessor, we'll say hashtag define, and then we have to give it a name, and the name should be in completely uppercase. So we can say keep RGB to HSV, and you can also specify a value for this macro. So for example, you can say 1 over here. And now what we can do over here is that we can use a if statement. You might already know this if you are familiar with Vex. A if statement, what it does is it checks for a condition, and if that condition is true, then it will run a code inside the curly brackets. So you first have to say if, and then in the brackets you have to specify the condition. So what we can do is copy this macro which we have specified over here and paste that over here. If that is equal to 1, then we can run this code. And let's remove this HSV to RGB line so that it only converts it to HSV. And now if you run it, you will see that this line runs and the condition passes, and we also convert it to an HSV type. So we will ask that how does that happen? Because if we don't do this define, then in this line is just something weird. So how is this working? So what actually happens in the pre-processing stage is that when we define a macro using this hashtag define, whenever it sees this macro name in our code, it will replace this with this value. So it is 1, as you can see. So what actually happens in the pre-processing stage is that it sees this, and then it knows that we have defined a macro for this. So it will replace this keep RGB to HSV in the pre-processing part and work as a text editor and replace that with this 1. And then 1 equals 1 is true. So this line will run and will convert it to HSV. And just like that, you can also define other things. So for example, you can define the value of pi. So you can say add hashtag define, and then you can say pi, and then you can say 3.14159. I think this is it. You can increase the precision of this, obviously. And then where you use this pi, it will be replaced with this. Now I can visualize it to you by setting it to this float 3 var, this pi value. So I can remove this and write pi instead here, and then remove this multiplication part and remove this RGB to HSV part. Now if you take a look at it with the inspect mode turned on, you'll see that we have the pi value for all of the pixels. That means that it is working. So now we'll try the Boolean define macros, using which we can remove this C++ specific if statement and use the preprocessor if statement. And to define a Boolean macro, what you have to do is just define a macro and then don't provide a value for it. So for example, we can just remove this keep RGB to ISSV, this one value from this macro, and now this if statement won't work. Now you'll see that it will start giving us errors because this flag, as you can see, the expression is not working because this Boolean macro doesn't have any value which we can compare. So what we can do instead of this C++ specific if statement, we can use the preprocessor's if statement. So what we can do is we can say if define, only then run this part of this code. And then to end this if statement, you have to use a end if flag. So remember, if def means if a macro is defined. If it is not, then this part won't run. And end if just closes a preprocessor if statement. And now this will run. And yeah, before doing that, we have to specify the macro which we want to check for. So we have to write our macro name over here. Is to HSV, and this will now check that if this keep RGB to HSV macro is defined or not. If it is defined, then only then this will keep this part of this code in the preprocessed translation or the compilation unit. If it is not defined, then it won't run. So now we can try setting the display flag on it. And as you can see, because it is defined, it will work, and now our RGB image is converted to a HSV. And you can try and comment this part, this this definition of this macro, and now this won't be converted to HSV. And instead of defining a macro, a Boolean macro or any kind of macro over here, you can also define it in the compiler flag over here. So in options, you have this compiler options, and you can provide options for the compiler over here. And over here, you can also define things for the preprocessor. And you do that by this writing this dash, and then say you have to write D. So you have to write this dash and then this D. And after that, you have to write the macro name. So it is keep RGB to HSV, and you don't have to, you can't add dash over here. You have to merge it with this dash and then D, and now it still works. Even if we remove this, you will see that this still works. We are not defining it anywhere in our code, but we are defining it in the compiler options. And you can also define numeric macros over here in the compiler options. For example, the pi one which we have over here, we can again visualize this by setting it to our this variables every component. So we can write pi over here, and then we'll remove this part and also this multiplication. And now it is obviously pi value, but we can remove this while copying this name. We can remove this and go to the and cooking this node obviously will give you error because now it doesn't know what this pi is. So we have to define it over here. So instead of this keep RGB to HSV, or we can just write another one. So again, you have to say this dash and then D, and then you have to write pi and then equals. Then you have to pass the value which you want it to be initialized with. So 3.14159, and now this should work. As you can see, we have the value and it is working. And there are also more kinds of this preprocessor flags. So you can also check if a macro is not defined using if ndef. It means that if a specified macro is not defined, then this if statement will run. And there are many other preprocessor flags which you can find on your own. And this is all I had to share with you in this tutorial. Thanks for watching. Like and subscribe. Dhanyavad.